have the presentation on fourth part of the hydrological modeling, that is flood peak estimation using hydrological models. So you must have heard in the news and also seen in the news these days, especially last 2-3 years, and including last 20 years, the excessive rainfall events has happened, and which has caused heavy flooding in the downstream areas. So if we include a broader category of the floods, these are the main reasons which I have listed here. First one is always the heavy rainfall. Second is dam break. For example, in few years ago, we had in the Southeast Asia and also in South America, some mining companies dam was there which broke. Sometimes normal water dams also they can break, and they can generate heavy flood in the downstream area. In 2008, if you remember, there was a severe flooding due to the breach of Kosi barrage at the border of Nepal and India. And if your river system is encroached upon by the unauthorized construction or congestion due to the heavy sediment load, which reduces the carrying capacity of the river, then the excess water is going to spill over its channel, and it is going to cause the flood. Then in India, we also have the cyclones in March, April, and in October, November time period in east and west coast of India. So during the cyclone, there is a heavy rainfall, and also there is a storm surge, so which can also increase the impact of flooding. Then in mountainous region these days, we have seen there are a lot of glaciers due to the long-term climatic changes. These glaciers are melting fast. So once they are vacating their ice at the end of their snout, that area is taken by the glacial lake. So this glacial lake is usually formed at the moraine, which we call the unconsolidated material, usually transported by the glaciers. So those can breach and cause the flooding. So these two photographs are example of the flooding in the urban cities, and also in the area near the Gorikond, where heavy flooding. You can see the flood marks have gone above, well above 10 to 15 meters in a deep gorge of Mandakini river. So as I told, the first and foremost reason for flooding is excessive rainfall. So apart from the dam break, or in February this year, we had the unique and unusual event of debris ice mix flow due to the rockfall in Himalayan region. So except to these two particular extreme events, most of the floods will happen during June to September time period. So when your soil is saturated and it is no longer able to retain the excess water, so whatever rainfall is falling on the land surface, it tends to run off and join to the river system. So if that intensity of the rainfall is very high, that tends to produce the flash flood, and if its duration is extended for 2-3 days, then it can also cause the long duration flooding, as happened in 2019, if you remember, in Bihar state, and also in November time period in 2015 in Chennai, and in September time period in Srinagar. Excessive rainfall, especially in dead monsoon period, caused the long duration flooding in these low-lying areas. So this is just an example of Northwest Himalaya, where we have less number of observational data sets. So satellite data can also be used to map the and quantify the rainfall with certain biases. Sometimes they underestimate, sometimes they overestimate the rainfall. So if we know that many areas are prone for flooding, so if we knowingly construct our homes or some commercial activities in the path of the river or very near to the river, these natural hazards, because floods are natural phenomena. So they can easily turn into a disaster. So the same thing is happening in many parts of the world where people have settled, because in last 100 years they have not seen any flooding in these rivers. So what happens, there tend to be sense of security, false security, what we call, that there is no flooding in this particular area, natural vegetation and other things are there. So that can cause the this natural hazard to convert into the disaster. One example is Rambara here, where entire township was washed away, and the highest casualty in 2013 Kedarnath floods was reported from this particular area. So this during the active floods, there is a big gap area which is due to the communication, real-time information, and day-to-day monitoring. So we cannot stop it because it's nature's own system of taking care of the planet Earth's weather system. So we can predict it, yes. Once we can predict it, then we can also manage and mitigate the effects by putting the formal regulation and other mitigation measures like structural and non-structural flood control measures. The non-structural will include the forecasting and prediction of these floods. Excuse me. So today's lecture on estimation of the flood peak is usually linked with the forecasting and prediction of the floods. So before going to the actual modeling, how we are able to estimate the flood peak in a given river system, there is one application of remote sensing, which is usually immediately after the floods, that is active flood mapping using the constellation of the satellites, mainly using the all-weather satellites like synthetic aperture radar. So this is one example of 2018 Kerala floods, when in this August month there was a heavy flooding in all the districts of Kerala, and many reservoirs were their gates were opened for the first time since their construction. So this light green, light blue represents the permanent water bodies before the flood, and these are the dark blue represents the flood pixels, which during that floods, excessive flooding was reported in these areas. So these activities are operational. So immediately after the floods, we know that what are the areas where flooding has happened. So in the plain areas, it is easier. In this particular image also, in the hilly areas, it is very difficult to find the flood pixels due to the effect of the topography and the vegetation. But in the plain area near the coastal, the flooding is easily identified. So in the hilly areas, how do we identify that what are the areas where flood has happened? So what we do, we take the pre and post image of the satellite data, generally the cloud free, and you can easily mark out the flood, high flood marks in the high resolution satellite data. So we know that flood wave or associated bank erosion or landslide, in this particular case of Rambara, they will show the distinct water marks. So if the water is normal here, so it will not encroach upon the sideway channels. And if there is a heavy flood, then it will erode away all the soil and water. That level of the flood marks are easily identified on the high resolution satellite data. So not just the Mandakini river, you can see the adjacent river valleys in the this particular this Rudraprayag and district and Mandakini river catchments. So you can see here these two adjacent river valleys also are having the distinct flood marks, which can be mapped, and we will know that these areas has also received heavy rainfall induced flooding. Same way, this area represents the Alaknanda basin, where from Badrinath we have Hanuman Chatti, and this is the Govind Ghat. So this is before 2013, 2011 image. It is showing in the normal before the floods, and if you see after the flood. So the main Alaknanda river doesn't show the flooding, but just below this Hanuman Chakti, this particular tributary and the tributary coming from the Valley of Flowers, both are showing the distinct signature of the heavy extreme rainfall. And people in media and in general public, they also call it cloud burst, but in technical meteorological term, we call it extreme rainfall, where within 1 hour the rainfall is more than 100 millimeters. So if that amount of rainfall happen, we will see while we proceed with the lecture, that this hilly area, when we make the land use land cover, so this is devoid of any vegetation in the higher reaches, and it also has snow and glaciers. So those three particular land use land cover classes, they generate very high runoff and very less infiltration as compared to the forested area or the other agricultural area found in these high mountainous regions. So same way you can see the impact of the flooding with the high flood marks here. So this is entire area above the what we can say Peri Dam, Bilanga River Basin. So here also, if you see the high resolution data, so this particular town Ghansali in the Bilanga River Basin, you can see here historically maybe 100 or 200 years ago, this entire river has this terraced floodplain is seen here, and you can see some river agricultural activities in these terraces. And then surprisingly, entire township is located right on those old historical floodplain terraces. So these areas, this area has also seen in last few years some major flash floods. And in future also, this particular township, and you can analyze and identify these townships very easily, which are located very near to the rivers, and using the geomorphological and other image interpretation techniques, you can identify that if there is a big flash flood in this particular area, so it can cause very heavy flooding. Similarly, this is the Srinagar town. Now there has been a dam construction here in this particular region, and this is Mandakini River Basin from Agastmuni onwards. So this is before 2013 and this is after 2013. So this is Rambada here, a big landslide you can see here. But you see this particular valley, this particular valley, this particular river valley, and this side, and other tributary of the Mandakini River, this side also. So because most of the tourists were located here, news of the damages came from this side. But if you see other river valleys also, there has been significant flooding in these river valleys also. So this remote sensing gives us the indirectly the ground truth, that what are the areas, because most of these river systems you will find the gauging system only at the Rudraprayag, or maybe some hydropower company has put near the Kedarnath area or near the Sonprayag. Otherwise, all these are the ungauged river systems. So if you want to estimate how much discharge is coming from a given rainfall, so it is very difficult to get this. So unless we know how much discharge is going to be generated in each of these watersheds, and then that water moves through these river valleys, joining to the multiple river system and then going forward. So all this necessitates the need for hydrological modeling, especially in these ungauged river systems. So apart from this, in hilly areas, we also employ popular topographical methods like height above the nearest drainage hand tool to get the first-hand information, that if the water level will rise by 0.5 meter, 1 meter, 2 meter, or 5 meter, what are the areas which are going to get inundated. So this will give you the immediate results, and that is the accuracy of this method is dependent upon accuracy of digital elevation model only. So this will also give you the fair idea what are the areas where the flooding can take place. And then if it is plain area, we know you can visit National Remote Sensing Site Hyderabad. where you can find the flood hazard based on the last 20 years of the radar-based flood maps. So if one pixel gets flooded each year in these 20 years, that will go under the very high flood hazard category. Otherwise, if it is getting flooding only once in 20 years, that will come under the very low. So that information can also be used. So apart from these reasons, these are the four major points which give us very advantage while doing the flood modeling. That is, the computer automation results in saving of time and resources. Flood insurance. Today, only the government of India has declared insurance which will cover floods, forest, this fire, and also the earthquake. So just like the agricultural crop insurance we have, all the people in India, they can take this insurance for which will cover all the man-made and natural disasters in future. So these insurance company will be requiring the flood hazard map to get those particular insurance rates. Then economic impact analysis, flood early warning, and design of the drainage control structures. So traditional methods of flood peak estimation are listed here, and the textbook definition of the flood is also given. A high stage in the river, which will overflow its bank and inundation of the surrounding area. So hydrograph of these extreme floods and stages corresponding to flood peak will provide very important data for hydrologic design. All these bridges, culverts, you these days, today also there is the news in the media that one flash flood has occurred in Lahaul district of Lahaul Spiti district of Himachal, and bridges have been washed away. So whenever we design any bridges across a river or culvert, waterways, spillways, dams, so we need how much maximum water can reach to the deck of the bridge, or to the safely discharged using the spillways in the dam. So they require this data sets for the full time series of the discharge, and for the outlet design, and for the scoring depth, and for the depth, how much height your dam should be located, or this bridge should be located. So you need the information on the maximum discharge that can pass through in a given river system or through the dam body. So there are methods like decimal method, empirical method, unit hydrograph method, flood frequency, and the hydrological modeling. So each method have its own advantages and disadvantages, but this unit hydrograph is a subset of hydrological modeling only. So if it is very small watersheds like the urbanized watersheds, then we generally use the rational method. Otherwise, unit hydrograph, which also has a limit that it should be less than 5,000 square kilometer. So this hydrological modeling makes use of the unit hydrograph, not just one, but synthetic unit hydrograph and other methods also, so that can be utilized to get the peak flood from the given rainfall data. So to derive this peak flood, we need to integrate various natural and man-made features into the virtual environment. So the most important characteristics which will define how much runoff will be generated, they are the physical characteristics of the catchment, and then climatic characteristics. So climatic characteristics represent the input data, that means the precipitation, the evapotranspiration temperature, and the snow characteristics. And the catchment characteristics represents the physical part, that is what is the soil type, what is the land use, land cover, what is the drainage network, how is the slope is variation, and also the elevation changes are happening in this one. So all this data, once it is geocoded, you can use the GIS to integrate this data into a single system. And in the climate, these are the data sets which have the variation in both space and time, whereas the physical data has the dominant variation in the space domain. The time domain, it can change, but not within a day. It can change land cover in the duration of maybe at a decadal scale, but not at the very event scale. That is when the major flood event happens, it is usually 1 or 2 days only, or sometimes within hours. So this data, once you integrate into a given system and then you add the time factor, it becomes my hydrological model. With then this movement of the water from the top of the catchment to the surface, subsurface, and then routing into the river system through the set of equation. We call it the hydrological model. So these are some of the database which is available to create these database for the hydrological models. One popular freely available extension is GeoHMS, that is Hydrological Engineering Center Geographical Hydrological Modeling System. So it is compatible with the ARC version, and these days some of these extensions are also available in the what we call the quantum GIS. So you can use either ILWIS. ILWIS also has a separate hydro processing tool where this automatic delineation of the river system, the watershed boundaries can be easily done, including you can do the classification of the satellite data to get the latest land use, land cover map. So we call this the GIS pre-processor. That means before running the model to estimate the discharge from a given storm or the rainfall, we want to see where physically it is located and how we can generate. So the basic input layer for this GIS pre-processor is digital elevation model only. Later on, I can add the land use, land cover, and the soil map to get the curve number, to get the initial values of the curve number. But those are the optional requirements you can add later on also. But initially, we need to have the digital elevation model, and if possible, location of the outlet where you want to delineate your watershed. And this layer, it is made in a system what we call ARC Hydro, this data model, which ensures the connectivity between the various layers. For example, if this river system is going in this particular direction, so it should be connected to the upstream as well as to the downstream nodes. So those connectivity issues are taken care in the ARC Hydro model. So this is the part where we generate all the input data sets, GIS preprocessor, and once it is ready, we export it into the main hydrological model, where we will be integrating the meteorological data and the other, it can be graded data, it can be point-based data, and then we will choose the options to generate the excess runoff, what is the losses taking place from the precipitation, and how the river routing to be done into the main hydrological model. So this hydrological model is a single platform which includes all the possible theoretically what we read in our hydrology textbooks, like the Syndes unit hydrograph, standard unit hydrograph, Esker unit hydrograph, that I will discuss in these slides. So it is a platform to do the basically event-based rainfall runoff modeling. People have used it for the long-term simulation also, but its primary purpose is to generate the event-based flood peak volumes. So this is the standard steps in a GIS preprocessor. So you get the digital elevation model, and then you follow all these DEM hydro processing options. If your area is a coastal area or having the low slope, then you can do some DEM reconditioning also. Otherwise, you can directly start with the fill sinks and then generating the catchment boundaries. And once you know the outlet of this one, so you can generate the new project, and then these options of basin merging, river merging, as per the user requirement of the minimum watershed area, they can be done. And this river length, river slope, basin slope, all these attributes will be automatically calculated. So this longest flow path, basin centroid, centroidal elevation, centroidal longest flow path, these are the physical parameters which are usually employed in the hydrology to calculate the cinders or the unit hydrograph parameters. Then there are the methods for calculation of the time of concentration, and the methods which are related to the rasters or the features, and the what we call routing parameters. So for the digital elevation models, as I told, you may have to use the existing stream data, or you can use the latest satellite image and digitize the river systems, and do the steam burning or the DM reconditioning options. And the man-made structures, although there is options available in the HMS model to represent all kind of man-made structures, including culverts, barrages, and dams, but still, if you want to represent those actually in the digital elevation model, you can generate the V-notch kind of structure into the terrain. Then the area where the flow is dominantly due to the groundwater, then in those areas your elevation has to be taken care. So once you export it, it will come to the main hydrological modeling system where the precipitation, if you are doing the simulation for the long-term simulation more than 1 year, then you have to include the temperature data so that your losses from the precipitation due to the evapotranspiration and other factors and infiltration, they are taken care properly. Once you put the air temperature data, you can use the Hargreaves or other standard unmanned mountain method to calculate the evapotranspiration. Otherwise, this precipitation will be subdivided using some empirical or semi-empirical models like the SCS method to generate the overland flow and rest water. There is also option for the channel infiltration, and then also there is option for the deep groundwater percolation. So the primarily, if it is a short duration event-based flood, then it will be the overland flow which will be coming to the stream channel, and then from this you can do the routing to get the discharge at the outlet point. So these are the various hydrological processes. You may not get the fully physical based model in this particular event, but standard hydrologic routing, and in some cases there is approximately you can use the kinematic wave model also in the runoff generation and for the routing part. So the input here is the precipitation, and there is a watershed is a hydrological system which will transform this precipitation into the runoff. So that runoff will be generated only if this infiltration and other criteria evapotranspiration is taken care, and we call this abstraction from precipitation. So that is the transfer function, this 5. And if there is some reservoir or some channel there, so this water will be delayed by adding this particular reservoir storage into this. So rate of change in the storage is equal to inflow minus outflow. And then once it moves into the river system, then you can see here in the hydrograph. The hydrograph, as you know, is the representation of the discharge in a river at a given point, where on y-axis I am representing the discharge, on the x-axis I am representing the time. So this particular part is known as the rising limb, this is the crest, and this is the recession limb, and this is the effective rainfall. And this bottom portion, we call this as a base flow component. So if there is a rainfall in this particular area, this is the hydrograph, as it will move downstream up to this point and then up to this point. So if there is a, for example, there is a dam here, so which is releasing the water, or there is a rainfall only happening in this particular area. So what will happen? The water channel acts as a storage. So there will be the attenuation in the flood peak. So this reduction in the flood peak due to the channel storage is called the attenuation. And then there is a delay in the headwater stream. The peak is coming very fast. That's why in the mountainous region, we call this as a flash flood, that within a short duration of time, your flood peak is reached. As you move downstream, the flood wave is reduced, peak is reduced, and also it takes longer time. So this is known as the time delay from the due to the presence of the storage in the watershed. So these are some of the models. There are 5 set of these models. Like the precipitation is the first one. Various kind of precipitation you can add. There is a loss model. How that precipitation, because here I'm showing this as a effective precipitation. That means if there is a 50 millimeter of the rainfall, that 50 millimeter will not get converted into the runoff. Out of that 50, maybe 20 millimeter is going to infiltration or evapotranspiration or some other depression storage. So the rainfall which is actually contributing to the direct runoff is known as the effective rainfall. So this loss model is the method which will decide how much of the given precipitation is becoming effective precipitation. Then once we have the effective precipitation, then we have the direct runoff model, so that how that effective precipitation is generating the water flow, and then how much is reaching at the outlet of the sub watershed. So once it reaches the main river system, that has to be transported from upstream to downstream. Then we use the hydrologic routing method. Then you can have the various confluences, bifurcations, or water control measures which can also be added. So once you export this, this is the basin model here, this is the explorer here. These are the various parameters which you can manually or automatically also you can get this once you export from the GIS component. So these, apart from this, when you run the model, you have to define the meteorological model. You have to add the time series for the rainfall discharge, paired data. For example, if you are using the unit hydrograph, that can be added, and the control specification. What is the duration of the duration of the simulation that you are going to run? So in the rainfall data, you can also use the depth area analysis in this particular model. So that can also be added if you want to do. Apart from the traditional rainfall hydrograph that we use for either from the satellite database rainfall or from the ground gauge observation. So you can use the frequency storm to generate the 100-year storm with the different year or different year return period. So this depth area analysis can also be done using this method. So these are the symbols which are used to represent the subbasin, reach, junction, source, sink, reservoir, and the diversion. And these are the set of time series data, paired data, grid data, and the methods of representing the precipitation. Okay. So the most common will be the specified hydrograph. So these are the summary of the various canopy method if you are using the evapotranspiration, or the surface method if you are using the infiltration, the loss rate in this SES curve number method, and green and this deficit and constant is very popular. In the transformation, most popular is SCS unit hydrograph and the cylinders unit hydrograph. And in India, unfortunately, we have very few unit hydrograph which has been actually generated using the multiple rainfall storms for the given observation, because maintaining a gauging site in these remote locations is very difficult. So mostly we use the cinders unit hydrograph or the SCS unit hydrograph. And base flow, any of this method can be taken, and for the routing, kinematic wave or the modified pull, this Muskingum-Kung method can be used. So these are the methods of runoff volume, direct runoff, base flow, and the routing models. And if you want to do the green, this long-term simulation, continuous simulation, then you have to choose the methods which are listed here. If you are doing the event only for the flood peak estimation, then it is the event and lumped and empirical fitted parameters can also be used with a fair degree of accuracy. So depending on your purpose, whether you want to use the satellite-based gridded data, or you want to run the longer simulation or the short duration simulations, you choose a particular method of runoff generation, base flow, direct runoff, or the routing model. So this is the overall flow chart. The GIS preprocessor exporting into the HMS, and parallelly you also generate the MET model, and you choose a particular method for loss transformation, and then you do the hydrological simulation. To aid the users, you can also use the this database storage system which will help you to organize your data in a much better way, and you can club this if you are doing the flood forecasting into the real-time system also. So if you have a telemetry system for the rainfall and other parameters, and including the water level from the rivers, so that can be this software can be used to directly read that data. So this real-time system can be utilized with this data set. So this is just an example of the precipitation data, how it is stored. And this is the schematic how this each subbasin will be represented, and then how the this routing will be taking place in the model. So this is the main summary, as I told, in the tabular format. So loss methods, surface runoff method, and then the flood routing method. So for loss methods, we'll focus on what parameters we need. If you are using the initial and constant, then you need this initial loss, constant loss, impervious area. Impervious area you can derive from the remote sensing data also. All the classes like having the urban or built-up class, the rock class, or the other class which is having very less infiltration rate, that can be classified as the impervious area. Similarly, if you are using the exponential, then the starting loss, initial accumulated rain loss, rate of change, and exponential of the loss is required, and impervious area in this case also. SCS curve number is most commonly used. For that, we do this in GIS preprocessor only by making use of land use land cover HSG, which is further used to get the curve number. Similarly, if you have the good soil data, you can utilize Horton methods and Greenham method also. So this is the rainfall hydrograph. If you are using the excess rainfall using this loss method, so below this line it is my excess this loss, and above this we have the excess precipitation, which will be used for the runoff generation. So this is the concept of initial and constant. Initially you assume high loss and this loss is usually linked with the infiltration capacity. So if you see the infiltration capacity curve, initially infiltration will be very high, then exponentially decreases. So that can be represented by, for example, this is a 10-hour storm. So for initial 1 hour, there is a high infiltration, high loss. Then later on, it is a constant. So this is the maximum infiltration capacity. Maybe it is reached there, and then up to this rate only the infiltration will take place. So this loss is represented using these two initial and constant loss rate. The curve number, as I told, depends on the land use, land cover, and the soil characteristics. A class here being the sandy soil, which will generate high infiltration, less runoff, whereas the D represents the clay soil, representing less infiltration and high surface runoff. So this also various classes, class 1, 2, 3 moisture conditions you can represent. So if it is a dormant condition, that is summertime period, then this limit for the rainfall is less. That means it is the less rainfall which will be required to generate the runoff as compared to the 2 and the 3. Similarly, if it is the growing season, it is vegetation will use a lot of water for its growth. For example, Kharif season, in that high amount of the rainfall is required to saturate the soil and also generate the surface runoff. So in that particular method, this antecedent 5-day antecedent rainfall in millimeters, this particular value is higher. So this is the example for the Holton's method. If you want to get this, you should have the infiltration rate growth index. This growth index can be calculated using normalized difference vegetation index. Then Greenham method, you need to have the soil hydraulic conductivity, porosity, and wetting strength. So in both methods, if you can get the high resolution soil texture map for your watershed, then both methods will work fine. Then for the surface runoff, this SCS method, this lag time runoff curve number, and this time area curve, time of concentration, storage coefficients will be used. So cinders can also be used, time lag and peak coefficient if they are provided. So this is a typical ordinate of the unit hydrograph. So this is the Clark's unit hydrograph. So this Clark's unit hydrograph, it can be generated very easily in GIS because we do get the length of overland flow. Once you know the velocity, you can easily calculate the time area curve, that how much time from a given area it will reach the outlet. So this can be very easily implemented in GIS. And if you are using the graded rainfall from, for example, TRMM, IMD, GPM, or weather radars, so that graded rainfall is usually compatible with the Clark's hydrograph only. So that gives the better result as compared to the other gauge-based rainfall sources. Then this is the Syndas unit hydrograph, where we are calculating this L and LC from the GIS, and CT is the coefficient representing basin storage, which is varying between zero 0.4 to zero 0.8. So this is the SES unit hydrograph, where it is dimensionless time and dimensionless discharge is there. The normal discharge divided by the peak discharge. So ratio of peak discharge, normal discharge to the peak discharge is taken, and also similarly with the time. So this can also be used. And you can also use the kinematic wave method, where this entire overland flow can be considered as a two planes, and for each plane you identify the overland flow length, and you also identify slope and the roughness coefficient. And once runoff gets generated from each of these planes, it will be collected by these conduits or the river streams, and then from the river streams this will reach to the main river. And later on, once it reaches the main river, you will be asked to get the routing method for this one. So for the flood routing, again, we have the Muskingum-Kung method, modified Puls method. So if you have the observation data, then you can use Muskingum and modified Puls method. If you do not have, then generally we prefer the Muskingum-Kung method for where you can provide the channel length, channel slope, and Manning's roughness coefficient. And so this roughness coefficient for the channel routing is different than the roughness coefficient what we identify for the overland flow used in the kinematic wave method. So you can provide single, and you can also provide the variable Manning's roughness length in a given river channel. So remote sensing, as I told earlier, in the SES method, land use, land cover, and soil maps are usually sourced from your remote sensing data, and from the Holton methods, NDVI is used for the growth index. And in the surface runoff, SCS dimensionless hydrograph, again you need the curve number, which is derived from the combination of land use and HSG. So GIS component is very strong. So all the watershed related parameters, the parameters related to loss method, Clark's method, and routing method, including length of the river, channel time, they are derived using the GIS based analysis. So this is one example here, and these are the list of the parameters or the water control structures which can be easily modeled in the HMS, right, including the reservoirs, orifices, and VF flows. So this is the graphical representation of the all steps, which includes DEM, soil, land use, getting the curve number, GIS processor processing the rainfall data, and finally doing the hydrological simulation to get the peak discharge. So this is the method where we have used the soil data from FAO, DEM from the GTOPO, and the rainfall data from the CPC. And if your area is bigger, then you may have to skip the UTM projection and go for the Albert equal or Lambert conformal conic projection. So these steps are very well known in the GIS community to derive the watershed and the stream systems. So you have the raw DEM, then you do the fill sinks, then you do flow direction, flow accumulation, and you get the stream grid. Then you convert the rasters into the vector format to derive the watershed boundaries map and the river boundaries map. And once you identify the outlet, the sub-basin or the basin boundaries will be automatically delineated. So this is one example of Mahanadi where we have put the outlet at Mundli Barrage. So this DEM, it may have certain errors, so they may represent the topography wrongly, which can be checked easily with the satellite remote sensing data to see whether the drainages are actually following the correctly, or there is some intermixing of the boundaries. So in this case, we have edited this boundary, and these days we have very good elevation models up to 30 meters publicly available from Kato's DEM from one. Then we have the ALOS 3 digital surface model. We have the Copernicus digital elevation model, Aster digital elevation model, SRTM. So if your area is not very steep, like the steep Himalayan terrain, this process will work in a fairly good accuracy. Apart from the naturally occurring steam junctions where the junction outlet is generated, the user can also add their own station. For example, these are the pink dots representing the station of Mahanadi Dam Authority and Central Water Commission. And then you calculate the longest flow path. So this longest flow path is a very handy tool because it is used to calculate the time to peak runoff, and which is related to time of concentration. So time of concentration is nothing but how much time it will take for the water from the farthest point in the river system to reach the outlet. So this is done at each sub watershed level. So once I know this longest flow length L, and I can correlate with the slope, I can calculate the TC. So these the parameters doing and calculating manually is difficult. So that is why these GIS tools are very handy. Then the next is centroid. So you can use any of these four methods, and in the latest version, we generally also prefer the center of gravity method to calculate the centroid for the given watershed. So from the once I know the centroid, it will also automatically calculate the length up to the outlet of the sub watershed or sub basin. So this LC, what is written here, this is also very handy, and it is used to generate the what we call the unit hydrograph basin lag for the Cinders unit hydrograph. So if it is first criteria is met, time lag is equal to 5.5 times the TR representing the effective rainfall duration, then you can use these two formulas to calculate the time lag and peak discharge. Otherwise, there is a slight change in these standard unit hydrograph if the time lag is more than this particular relation of effective rainfall duration. But in both the cases, we have to use the LC and L component, one representing the longest flow path length, the other representing the distance in kilometers from outlet to the centroid. So this information is directly used for our unit hydrograph generation. So once you have done this, then if you are doing the routing using the Muskingum-Coombe method, it will ask you the bottom width, side slope, and Mannix N also, so that you can do with the help of satellite data and digital elevation model for each sub-watershed. So these are the some of the reach bottom width for each of these sub-watersheds. And for the curve number, you don't have to go outside the GIS environment. There is a inbuilt functions there where you can do the union operation for land use and soil to generate the curve number. And there is a standard table format which you need to add your standard curve numbers from the textbook. Once you add this the land use, land cover, and soil, this is the table format where you have to add into the GIS. This is the soil map, and this is the table for the soil map, and here you are given the option of representing the various soil texture. For example, you know the percentage distribution of sand and clay or the silty soil. For example, seal loam. So you can say A part is 50%, B part is 50%. That curve number will be given the weightage based upon this hydrologic soil group. And then you union this land use and soil map, you will get this. And then there is a utility in the GeoHMS, or you can generate outside also if you want to generate the curve number. So this curve number usually represent the curve number 2, representing AMC condition 2. So once we have this curve number, I can easily calculate the basin lag and time lag, which will be further used in the SCS unit hydrograph as well as the cinders unit hydrographs. And this once I have generated this curve number, there is a inbuilt function related in the GIS, which is TR55 method, technical report 55, where each watershed is divided into 3 parts to calculate the time of concentration. The top from the ridgeline to 100 feet or 300 feet by default, you can change this. It is considered as a overland flow, that means sheet flow. From that 300 feet up to the centroid, it is considered as a shallow concentrated flow, or what we call the interflow. And then from the centroid to the main outlet, the water is assumed to be moving in a river channel. So these representing different colors, like the blue one, they are taken directly from the GIS. The green one a user will provide, and then finally this white one will be computed, and for each of the sub watershed you calculate the summation of TC by this sheet flow, interflow sorry, and overland this channel flow. So once this time of concentration is found, we can use various methods, as I told previously, to calculate the basin lag as 0.6 or 0.7 of the TC, and then later on you can calculate the Q peak also. And once you have generated this, populated this Excel sheet, you check for the units and data compatibility in various coordinate system, and you then export. So once all the steps are there, these many files will be generated. And these are the steps which we use to generate the gridded rainfall. So most of the gridded rainfall, if you download from the various space agencies like PRMM, GPM, or ISRO, MOSDAC, you will find them either in NetCDF format or in HDF format, and sometimes they are also given as the TIFF files. So usually we have to stack them to get the full time series, and then subset them, do the zonal statistics at each watershed level, and then generate. So this is one data CPC which is available at 10 kilometers resolution or 0.1 degree, and this is available at daily time scale. So this has been used. So once this header information you are able to read this, we make the stack, and this for entire Maharadi basin we calculate the rainfall for each watershed. And we can also use the DSS system here to represent this data. So once all these physical parameters and subbasins are generated, MET models are added, we export it into the HMS model, and this is the schematic of HMS model. So there are two sets what we have used here. One is Clark's unit hydrograph transformation and kinematic wave routing. Second is SES curve number with the Muskingum convoluting method. And this is the base flow components. So there are various combination what we have attempted in this particular case, where we are using the SCS method, or using the Clark unit hydrograph method, or we are using gauge data plus the CPC rainfall data only monsoon season, or taking the full duration of the year. So these four combination, this combination 3 has given the most promising result for the one of the watersheds, so which is above Hirakund Dam, because you can do this simulation for full basin, but if your basin is having lot of water control structures, man-made water control structures, you have to give the actual outflow rate, so which may not be feasible at all the locations. So within this here also there are small dams and check dams also, so which will attenuate and cause the storage of the water. So unless you are able to represent all these internal storages correctly, your accuracy will not increase more than 50 or 60%. So that is the thing that you have to take care into account whenever you do the hydrological modeling for the flood peak. If your study area is very much downstream, then you have to consider the outflow rate from the dams. For example, Maharashtra floods in the Western Ghats. So Maharashtra has the highest number of reservoirs in India. So whatever the floods it is caused, it is not just simply rainfall runoff. The water is also released by the dams because they are already full. So those has to be considered whenever you make the flood forecasting system. So the same method of the flood peak estimation was employed for the Kedarnath area. So this is the initial estimate for the hydrograph, where we use this photograph and do the reverse way, that this is the maximum width, and then assume certain velocity and depth of the water to get the total hydrograph. So this is the catchment area of the Mandakini River up to Sonprayag, and we have seen the ester DM to be the better than the other DMs as compared. You can see here some gap filling has been done due to the steep slope in SRTM. And Cartosat also, there was certain errors in this particular steep valley, because Cartosat may not give you very good results if the valley is very closed, or the elongated shape of the valley and dense vegetation. So in this case, we have used the Ester digital elevation model. So these are the steps here, and these are the catchments. So initially, when we did this exercise, here we delineated multiple sub-watersheds with the small scale. So what happens if the basin lag is smaller than the what we call the rainfall data? The input rainfall is daily, or at maximum it will be available at hourly time scale. So your effective rainfall duration also, it is 1 hour from the observation data. But your basin, because your area is very small, so your time to concentration is very less. It is less than half an hour, in some cases 15 minutes. So this will cause very less basin lag. So we cannot use the traditional rainfall data here. So to avoid such problems, hydrological issues, what we do, we subdivide the watershed into the two locations, main Sonprayag here, second at Rambada, so that this time of concentration and time lag is little higher in hours as compared to in minutes what we are getting earlier. Okay. So here you can see here, this is one at Rambada, another at Sonprayag. So I can use the hourly or 3 hourly rainfall data to generate the peak runoff volume. So this is the runoff volume which has been generated using the kinematic wave, because this area will not give you the accurate results if you use the traditional SES method. So here we make use of the kinematic wave, subdividing the catchment into two planes, one plane representing this side, one plane representing this side, and this overland roughness length is less here because no vegetation, so very high runoff can be generated. So on the 16th of the evening, when the main flood wave came, you can see 600 cubic of the water is generated at Rambada, and by the time it reaches the Sonprayag here, the total catchment area, it is 900. So next day on the 17th, due to the glacieric outburst flood of the Choraburi Lake, the peak flood is estimated at 1100 cubic. So first flood wave was also very much damaging on Kedarnath and Rambada stretch, and that was worsened on 17th morning when the lake breach happened on this particular part. So the same study was extended to estimate the peak flow rates, inflow rates into the Tiri reservoir. So on the 15th to 18th July, so this is the observed flow, and this is the simulated flow, what we have estimated using the SCS curve number method. Only thing here, one problem can come is the presence of snow and glaciers. Although during the monsoon time period or during the June, most of the snow will be melted, only permanent glaciers will be there. So they also represent the delayed flow, because they will not immediately generate the runoff. So there will be delay of few years. So this time of concentration will be little higher for these catchments as compared to the non-glaciated catchments. So this is the calculated and observed file. You can see more than 7,500 cubic of the water inflow was generated in the Tiri, but the outflow from the main Tiri dam was only 500 cubic. So we did this same exercise to cover the Alaknanda part also. So Alaknanda, more than 12,000 cubic water is getting generated. So if both the waters are coming without the Tehri dam, it would have been very damaging to Rishikesh and Haridwar area. So effectively, this Tehri dam acted as a storage, and then it actually saved the this downstream areas of Devriyag, Koteshwar Dam, and Rishikesh and Haridwar township. So the same study has been extended as part of our ISRO-sponsored disaster management research and development activities, where we have done experimental flood early warning by taking the input from the weather forecasting model, our own, plus using IMD's forecast model also at 3 kilometer resolution. So that is gridded rainfall is added into these sub-watersheds, and the runoff volume and the hydrographs are generated. So because this is experiment, we are not able to get the steady outflow rate. So these are the virgin flow outflow. So if there is a very heavy rainfall in the catchment, we can easily predict 3 days in advance how much water is going to be generated, because most of these watersheds are ungauged. And the similar exercise is done to the Satluj Basin, Beas Basin, and Jhelum Basin also. This is one example of the Beas Basin. So in the Ganga river, we do not have the sufficient data to calibrate all the flood events of last 5 years. But in the Beas Basin, we do have the data from Bhakra Beas Management Board, which has provided us the hourly discharge data at Sujanpur, Tira, and Nadon. So this is the HMS model for this. And this data we have used, and we have simulated the peak flow at the time step of 1 hour, 6 hour, and daily. So the model performance when we match with the actual discharge, because in the hilly areas in one day there can be more than one flood wave, and if you take the 24-hour average in a hilly area, it will not represent the accurate peak flow that might have crossed through a river system, because the peak flow may occur only for few hours. So in this particular case, we have used the hourly time scale, and then it has given very good results for the two major flood events of 2014 and 15, where it has matched well. Mainly, we have used the combination of the data. That means we have used the actual rain gauge data, which was also available at the hourly time scale, and also we have used the satellite based data, which is available at 3 hourly time scale. So if your input rainfall data is very good and you do the extensive calibration of these data sets, you can get the exact match to the flood peak. And if you take the daily data, you may get the flood peak as 2,500 or 3,000, but actual flood peak you can see here on the 15th August 2014, it crossed 7,500. Okay. So this is 2014. Similarly, for the 2015 also, during 5th to 8th August, there was a heavy rainfall. So there also you can see 6,000 here and 7,000 in the down side. We could get the exact match with the simulated and the observed flood peak. So this represents today's lectures, and these are some of the internet-based pictures of the ongoing floods and floods which has happened in the July month itself. So representing the Europe, Germany, here the Maharashtra Konkan area, you can see the rivers in the very flooded condition. So after 3 days, the water will come normal. The hydrograph will be in the recession phase. This is the China floods. So all these floods are caused by extremely heavy rainfall for a shorter duration time. And so such kind of methods, because these days, as you must have seen, meteorological forecasts are very good. So Himachal has been given the red alert in 5 districts for today and day after tomorrow. Similarly, Maharashtra also under the orange alert. So meteorological forecast is there, but how that water gets translated and moves in a watershed, river basin, and moves in a river system, that is very important. So if we are able to correctly predict that particular water, how it gets generated in a river system, and tomorrow in continuity to this, you will have the flood inundation modeling. So how it spreads once it comes into the river channel, how it spreads in the floodplain area. So tomorrow that will be covered by our fellow scientists. So with this, I cover complete the hydrological modeling flood peak estimation lecture. So floor is open for questions now.